Our next speaker is Dr. Rob Burgess from Medical Technologies, Inc. And it's really a real pleasure to welcome Dr. Burgess back to his second Unither conference. We heard some really exciting results from him last year, and just speaking briefly last night, it's exciting to know that we are going to gain access to some new unpublished research that his group has done since last year. The topic of his talk is carbon nanotube-based therapeutics. Please join me in giving a warm welcome to Dr. Burgess.
Thank you, Dr. Rothblatt. I really appreciate the nice introduction. And thanks to you and Dr. Blumberg, as well, of course, as to Temple and Genesis for organizing yet another wonderful conference. Obviously, this is my second time to talk here at this conference, and I'm very delighted to be back this year. I think my talk perfectly complements Dr. Quintera's talk on the solubilization and the use of carbon nanotubes as drug delivery vehicles, but I'm going to focus more on the carbon nanotube itself as the mechanism of therapeutic action. Sonia, since you gave a description of carbon nanotubes, I do appreciate that, and I don't have a slide that does that, so thanks very much, and I'll skip over that. So what I'll do is I'll give a brief background on the history of the formation of medical nanotechnologies as a spin-out from Richardson-based Zyvex Corporation, but I'm really going to focus the majority of the talk in a data-heavy fashion, reiterating some published data as well as some more recently unpublished findings that Dr. Ellen Vitetta and her colleagues at UT Southwestern was nice enough to share with me for this talk. So medical nanotechnologies was a spin-out that was formed as a result of a splitting up of Zyvex Corporation about a year and a half ago. Zyvex is based in Richardson, Texas, and one of its subsidiaries, now based in Ohio, called Zyvex Performance Materials, has developed a technology for the very efficient dispersion of both single-wall nanotubes and multi-wall nanotubes and attachment in a variety of host matrices, primarily for industrial applications, and they're focusing mostly in the sporting goods area. And so they've found methods to effectively disperse carbon nanotubes and attach them to host matrices such as epoxies and polyurethanes and utilize their unique strength capabilities and the lightweight properties of carbon nanotubes in such things as sailboat masts, the necks and shafts, the necks of baseball bats and shafts of golf clubs, and in bicycle frames. And utilizing carbon nanotubes in this fashion, what you see on average is a decrease in weight of about 80% in comparison to steel, and an increase in strength about threefold, so threefold stronger than steel. So you see a lot less snapping of the sailboat masts. You see stiffer bats in which you can put the weight of the bat in the head of the bat, and you can put the weight of a golf club in the head of the club, increasing the distance that the balls hit, but maintaining the accuracy because you have a stiffer shaft. It's obvious why you would put this in bicycle frames to reduce the weight and increase the strength. What does this have to do with medical applications? I'll get to that in just a second. This is the technology. It's a molecule called Quintera, and it's a bipartite, bifunctional domain-based technology in which one domain of this molecule interacts through non-covalent interactions with the carbon nanotube, either single-wall or multi-wall. It's non-covalent. It's primarily through van der Waals interactions. And this allows for a dispersion or a displacement of the tubes away from one another. The second domain is a domain that can be customizable and binds to the host matrix, like an epoxy or a polyurethane, and really allows for a dissolving of these exfoliated carbon nanotubes in a very thorough fashion. So you get thorough exfoliation and uniform dispersion, which makes them very valuable for industrial applications. So we also looked at whether or not we could manipulate the Quintera technology to disperse carbon nanotubes in an aqueous environment. Given the unique properties of carbon nanotubes, this would give us an opportunity to consider them in a therapeutic fashion. So what we have here are a couple of scanning electron micrographs and a couple of vials of carbon nanotubes in water. This SEM is as they come from the manufacturer in a really bundled kind of ball of twine type format. This SEM is carbon nanotubes dissolved in Contera, in which the side chains have been custom designed to interact with water molecules. It's very hydrophilic. So this is in water. In the absence of Contera, this is in water in the presence of Contera. And they remain soluble for weeks on end, probably close to a month, and then they start coming out of solution. So this now allows us to look at carbon nanotubes for biomedical applications, but it also allows us to consider the attachment of targeting agents for carbon nanotubes to seek out unwanted entities within the body. And so we performed some studies with collaborators down at MD Anderson Cancer Center, specifically Chris Gannon and Steve Curley. And this graph represents a change in temperature versus time upon exposure to an RF field. And as you know, carbon nanotubes are sensitive to radio frequency waves as well as near IR light. This graph is the water alone. You get a little bit of heating in the presence of RF. This graph is carbon nanotubes that are not in the presence of Contera but are in the water in an insoluble format. And this graph is carbon nanotubes that have been exfoliated, dispersed, and dissolved using Contera. And what we're seeing here is the most efficient heating, on average about 5 to 7 degrees per second centigrade in the Contera dissolved carbon nanotubes that are in the water. This diagram was taken with permission from John Kanzias, who's a pioneer in the use of RF fields to excite nanoparticles for therapeutic applications in the cancer area. And so what he's done basically is he's focused RF fields and nanoparticles, including our carbon nanotubes, in which he injects the tubes into a tumor and then exposes the tumor and the carbon nanotubes that have been dissolved in water using Contera to a radio frequency wave at the medically approved frequency of 13.56 megahertz. And the goal here really is to ablate the tumor tissue through thermogenic application. So it's a heated ablation. The tubes are very sensitive, as you can see, and they heat up very rapidly in the presence of that field. In addition to that, and you heard a little bit about this just a minute ago, carbon nanotubes can be functionalized with targeting molecules. And some of this data is unpublished, and some of it I presented actually at the last conference. They can be functionalized with lipids, and that is attached with lipids such as polyethylene glycol or PLGA, which would allow for the dissociation in water. And they can also be functionalized with the attachment of antibodies. So what we have here is atomic force microscopic image of carbon nanotubes that have been dispersed in the lipids. This is a transmission electron micrograph of carbon nanotubes that have biotin attached to them through those lipids. And this is unpublished data of an atomic force microscopic image of carbon nanotubes that have antibodies actually covalently attached to them. So they've been dispersed, but they have antibodies covalently attached, non-reversible binding, so these will not be detached from the carbon nanotubes. In addition to that, our collaborators at UT Dallas, Rocky Draper's group, has shown that carbon nanotubes in the presence of this polymer, P.PSS, which is also used for the dispersion of these tubes, tend to enter cells at a very high rate and accumulate at a very high concentration. This is simply bright field microscopy of HEC293 cells, which is a human kidney cell line, in which the media has been doped with carbon nanotubes dispersed in this polymer, and the cells take up the carbon nanotubes and exhibit that at very high concentrations. This is actually a couple of cells undergoing mitosis. You can see the carbon nanotubes surrounding the nucleus in the cytoplasm, and the arrow indicates a very dynamic environment. The arrow focuses in on one particular carbon nanotube cluster. And we think, although we haven't confirmed this, we think these are vesicles, which would suggest that the uptake is via non-receptor mediated endocytosis. And we're in the process of confirming that now. But it raises a couple of points. This would allow carbon nanotubes now to deliver a drug or a therapeutic within a cell, but it might also allow for better or more efficient thermal ablation of cells, as cells may be more sensitive to temperature changes within the cytoplasm as they would be if the carbon nanotubes just surrounded the plasma membrane. So carbon nanotubes, we think, make a very unique platform for therapeutic intervention with respect to cancer. Have a very organized and well-known structure, and the mechanism of action here for cancer treatment is known, which is a real advantage as far as the FDA is concerned. Sensitive to radio frequency waves as well as near IR light, and they're electrically, but much more importantly for this case, thermally conductive. They emit heat when you expose them to these external fields. They can be functionalized with some molecules. I'm going to show some of that data in a minute, and I've just shown that they can penetrate cells very efficiently. Regarding toxicity, we've looked at the Contera molecule, and we see virtually no toxicity. These are graphs of an increase in the Contera molecule concentrations in a Petri dish versus cell numbers on the dish. This is a graph of carbon nanotubes dispersed in Contera and cell number. And what we can see is virtually no toxicity with Contera, no matter what concentration we increase to. We do see about 10% death when we get up to very high concentration of carbon nanotubes, around 25 micrograms per mil. But the therapeutic range of concentration of what you would inject into a patient is much, much lower than that. And so we really don't see this as being an issue. And this, again, is cell type specific data. So in addition to that, I've got some more data here, some of this unpublished on binding as well as cytotoxicity. This is the coupling of an antibody called, I believe it's called RFB4. And this antibody binds specifically to the CD22 receptor, which is expressed very highly on B lymphoma cells known as Dowdy cells. This is a typical chromatographic separation, and this is the antibody coupled to what's called Neutravidin, and this was used for these binding studies. Toxicity studies, when you look at an increase in concentrations of this in the presence of tritiated thymidine uptake, this measures DNA synthesis, and therefore it measures cell proliferation. We basically see no toxicity of the avidin, no toxicity of the antibody, and no toxicity of the antibody-avidin conjugate. In addition to that, we can show that we can saturate, and that is we can bind every cell in the Petri dish at very small concentrations or additions of amounts of the actual antibody and carbon nanotubes attached to those antibodies. This is about 0.237 picograms added, and it gives full saturation of the actual binding to the cells. And this is a fluorescence image of that, in which enhanced green fluorescent protein was attached to the carbon nanotubes and the antibodies, and you can see virtually every cell lighting up. So expanding on those studies then, what we could see here is we're looking at the B lymphoma cells and another cell line, peripheral blood mononuclear cells that's been activated to express CD25. These cells express CD22 but not CD25, and vice versa for these cells. The RFB4 antibody only binds to CD22, not CD25, and vice versa for the RFT5 antibody. The antibody binds well, the antibody plus the avidin conjugate binds well, and the antibody plus the conjugate plus the carbon nanotubes bind very well, as evidenced by staining for the antibody or staining for the carbon nanotube. This nonspecific antibody doesn't bind, and you see the exact converse in this panel. CD25 specific antibody binds, the antibody plus avidin binds, the antibody plus avidin plus carbon nanotubes binds very well, and that's confirmed both by looking at the antibody and by looking at the carbon nanotubes. But the RFB4 antibody, which recognizes CD22, does not bind effectively to these cells. So cancer-based therapeutics, Dr. Ellen Vitetta's lab at UT Southwestern focused on the use of near-infrared light in the range, I think, of about 820 nanometers to specifically ablate targeted cancer cells in a Petri dish. She showed that in the B lymphoma cells as well as the peripheral blood mononuclear cells. So what we can see here again is we're looking at tritiated thymidine uptake, which measures cell proliferation. You can see the control. This is the baseline here in the presence of the antibody plus the carbon nanotube exposed to near IR get a decrease in DNA synthesis and proliferation. In the presence of a nonspecific antibody, you don't see that, and vice versa. When you target these PBMCs, it's only with the antibody that binds to that particular receptor on the surface of that cell that you actually see efficient ablation, which is right here. You don't see that with the antibody that binds to CD22. And this is just a stability study. These conjugates were made and they were incubated at 37 degrees Celsius for 1 day, 2 days, and 3 days. And then we looked at their utility again for ablating B lymphoma cells, and this is using the RFB4 antibody. And what we can see is they're still quite effective even 3 days out. So it suggests that the complex is stable. Our collaborators at MD Anderson Cancer Center performed a similar experiment with the pancreatic cancer cell line PANC1, in which they looked at the survivability of these cells upon exposure to RF for 2 minutes. So this is a flow cytometric analysis, and the channel M4 represents all non-viable cells. Channels M1, M3, and M2 represent different phases of the mitotic cycle, so cells that are healthy and dividing. And what we can see is that in the Petri dish, upon exposure to RF, in the presence of carbon nanotubes, you get 99.7 propydium iodide stained cells, which suggests that the majority of the cells have been ablated, but only in the presence of carbon nanotubes. This was expanded upon in New Zealand white rabbits, and so these are rabbits that have been injected with VX2 tumor cells. Tumors have been allowed to grow to a certain size, and then we've used Kantara solubilized carbon nanotubes or just Kantara and injected locally into the tumor. We look by tunnel assay, which measures both apoptosis and necrosis, and we look by hematoxylin and eosin staining, which measures, which just stains the cytoplasm and the nuclei of the cells. You can see is massive cell death in the presence of the carbon nanotubes and RF for 2 minutes, and you don't really see that here. There's one necrotic cell that we see. And in H&E staining, you can see massive ablation of the tumor itself, and the arrow just indicates really a lot of coalesced carbon nanotubes. In the presence of Kantara, we don't see that. In fact, we see active division of the cancer cells. So what we'd like to do now at Medical Nanotechnologies is really take some targeting agents from 4 specific classes, and that is monoclonal antibodies, small molecules that could be synthetics, aptamers, which are nucleic acids that bind specifically to interesting targets, and then small peptides. And some antibodies, as well as small molecules, have now been approved as targeting agents, and we'd like to utilize those to target, for example, the HER2 receptor or the EGF receptor. This aptamer is in development. It targets and binds to nucleolin and actually gets transmitted all the way into the nucleus. We think this would be really interesting to try to deliver carbon nanotubes to the nucleus. And finally, the RGD peptide targets the integrin receptor, which is overexpressed on a variety of tumor cells. So I think thus far what we've shown regarding functionalities, we can disperse carbon nanotubes using Kantara, PDOT, PSS, as well as lipids, and that some of those dispersions remain stable and functional in an aqueous environment for a large amount of time. We've shown efficacy in vitro and in vivo. We can kill cells in vitro, we can target and kill cells in vitro, and we can kill cells in vivo, and that is in tumor cells through localized injections in rabbits. Toxicity, our initial tox findings do suggest that in the kidneys, the carbon nanotubes are cleared very quickly on the matter of a few hours. Our PK studies that have been published by our collaborators down in Houston are very encouraging, but we have not done the biodistribution studies in tissues. And I realize that it's a very controversial field. The way we look at it is if you have a patient that has 6 weeks to live because he's got a glioblastoma, and you could do the surgery and then come in behind that surgery with this type of technology and wipe out a lot of the remaining cells, that patient's probably not going to care too much if there's an asbestos-like effect if you give them another 6 months or a year to live. And so we are big fans of this technology, even if it is somewhat toxic. And finally, specificity. We've shown that we can target very specifically in the Petri dish, and we would like to take these studies to the next level as other groups have, and show that we can target in a live organism and kill cancer cells. And so I've acknowledged most of these people during the talk, but I just want to thank again Ellen Vitetta and her colleagues, Radu Marshas and Pavitra Chakravarti, for allowing me to share the unpublished data. And I want to thank Jim Von Air and Zyvex Corporation for allowing us to spin this company out. And I'll just finish with, we are seeking financing. We are always undergoing rounds of financing, and it's very expensive to perform these types of studies. We cannot continue this exciting work without the proper capital. So if you're interested in investing in this company, I would love to speak with you, or if you know of investors, I would love to hear about them. Thank you.
Great presentation, Rob. There's several people lining up at the microphones, which very good indication. You've done a great job. So again, please introduce yourself and whichever organization you'd like to affiliate yourself with.
I'm Mark Kester, Penn State College of Medicine. Excellent talk, Rob.
Thank you.
So intratumoral injection is great, but when you talk lymphomas, leukemia, when you talk metastases, you're really talking systemic delivery systems. Have you used some of the great animal models for orthotopic PANC1, pancreatic cell growth in animals, and or some of the B-cell lymphoma leukemia models to actually look at systemic delivery of these carbon nanotubes?
No, we have not, unfortunately. And what we've been focusing on is solid tumors to date, primarily due to funding issues. It's interesting that you bring that up because our previous collaborator, John Kanzias, has been focusing quite a bit on solid tumors, but he also has been looking to optimize the system to treat circulating types of cancers like leukemia. So we think theoretically it is something that can be accomplished, but we just need to focus on that at a later point.
Ennio Tasciotti, Division of Nanomedicine in Houston. Great talk. We work with Steve Curley on the delivery into the liver, so I'm very close to that. I don't want to play the role of the devil's advocate here, but I want to just make a comment, maybe a little provocatory. I understand the willing decision of getting an injection of carbon nanotubes if you have a tumor and you don't care about the consequences. I just wanted to know what is your opinion about the environmental exposure. Being you're in a company, you're exposed to this type of material. So what is the policy that you envision for the future for just...
Yeah, I mean, I think you raise a good point, and I would just like to say that when I was at Zyvex, our scientists and researchers there handled the carbon nanotubes with utmost care for safety. You know, obviously there could be long-term effects upon exposure to these, but thus far we haven't seen any detrimental effects, and to my knowledge, there have been no humans that have come down with any detrimental effects due to exposures to carbon nanotubes. You know, that being said, from a therapeutic perspective, I realize that the biodistribution and PK studies need to be done in animals. It's a very high priority. I don't agree with the asbestos findings. I think the concentrations of the carbon nanotubes that were used were way too high, and I think most scientists would agree with that. But chemotherapy is a poison, and it's approved by the FDA, and it still works, and it does help people to live longer and live better lives.
Rob, Jay Yadav from Cardium, was a very, very interesting talk. What is the first? What is the first cancer you're targeting?
So the first cancer that we've looked at targeting is pancreatic cancer, because it's one of the most devastating solid tumors that are out there.
And you're going to use RF as your energy medium, or?
That's the RF was deep tissue penetrating. Now, whether or not it has detrimental effects to the pancreatic cells that are not cancerous, we don't know.
Right, that's what I was wondering, because when you showed that nice slide with the apoptosis, I didn't see a slide with just RF.
So we've done that. I didn't show that data. We haven't done it. Steve Curley specifically has done it, and as far as he can tell, we don't really see any effect. But I do think that needs to be looked at further. You know, we interact with RF fields every day when we walk under a radio tower, and And thus far, I think there hasn't really
No,
been.
I understand that. I know a lot about RF fields.
Right.
What I'm asking you is, what is the coupling? What is the coupling efficiency of the nanotubes versus surrounding structures for RF? Is what I'm trying to get out.
Coupling efficiency of the nanotubes versus.
Exactly, because your body absorbs RF too.
Right,
Water,
right.
right? So that's what I'm trying to understand. What is the differential absorption? What maybe you haven't done this work yet. What
Yeah.
energy levels are you
So I know that.
operating at, and what is getting absorbed?
What I can tell you is that the frequency is medically approved 13.56. It's 2 minutes exposure of the entire animal. It's a
Okay.
pancreatic tumor, and we see ablation. This is not targeted. This is localized, locally injected. So there's no antibody that seeks out the pancreatic cells. But we are seeing considerable cell death within that. Now, how much the carbon nanotubes clear themselves from the system after that treatment, we haven't looked at.
So a fairly brief time period. What kind of power levels are you?
I can't recall what that is, unfortunately.
No, very interesting. Thank you.
Thank you, Jay.
Shri Sridhar, Northeastern University. Enjoyed your talk. Let me preface by saying that I'm a big fan of hyperthermic treatments, but the issue that my clinician friends bring up with me is actually not with the RF fields itself. We actually, and in our case, the nanoparticles are iron oxide nanoparticles, which are federally approved, and they work at lower frequencies. But the real issue, they tell me, with these hyperthermic treatments is localization of the heat. And and they tell me that without any without a guarantee that the temperature will not rise enough to induce coagulopathies and heat the surrounding tissue beyond 43 degrees, that they see essentially very little chance of success of these type of hyperthermic treatments. So I'd like to know, what you think about that and how you may address that issue.
I think that you're hitting again on Jay's point of what is the effect of RF on the entire organism, whether it be a rabbit or a human, in the absence of the carbon nanotube.
No, I'm not talking of the outside. I'm saying that the RF couples to the nanoparticles, not to the surrounding tissue. I think the surrounding tissue coupling is very weak. That's not the issue. So I think here there's a difference between the previous question and mine. The question is that when you heat up the nanoparticles locally, you actually heat up, the heat is conveyed to the surrounding tissue,
Right.
Not just the cancerous tissue, but the normal tissues.
Right.
And they tell me that this is going to be a critical issue,
Yeah.
and we're thinking very hard about how to address this.
Yeah, so or rather our collaborators, Steve Curley and Chris Gannon and others, have focused on that by testing short bursts of RF, which would heat up the carbon nanotube attached cells within the tumor, very localized and very brief, just enough to kill the cells and hopefully minimize the damage to surrounding tissue from the additional heat. So a modification of the amount of time in which the RF is delivered, and also there are prototypes of RF devices that focus the RF like you would near IR light, which would minimize the exposure to surrounding tissues. I hope that kind of got at your question.
Hi, Dave Zhang from Caltech. I'm just wondering, what happens to the carbon nanotubes after you do the whole RF and then cell ablation? Do they stay there and seek out another cancerous cell target and go in again, or?
Yeah, we haven't looked at that, but the carbon nanotubes are extremely stable. Now, whether or not the antibodies themselves become not dissociated, but maybe denatured upon the exposure to the high levels of heat and then make them inactive, that remains to be determined. But my guess is they're going to be less efficient at targeting the next cancer cell, and eventually we would like to see that they're cleared from the system.
Right, so how fast does it clear from the system?
Yeah,
Yeah.
we've shown that it clears from the kidneys in a matter of about 8 hours. But as far as biodistribution studies, we haven't done those yet.
Thank you.
Bruce Blumberg again. Could you tell us something about how many nanocarbon tubes you can make? As you know, there's a contemplated project for a space elevator, which would be in orbit 600 miles, geostationary orbit. And the hope is that they'll be able to use carbon tubes.
Right.
What
Well, I
is-
know, I know that multi-wall carbon nanotubes can be synthesized very economically and in large gram quantities.
Right.
Single-wall carbon nanotubes, which is what we prefer from a therapeutics perspective, because the structure is well known and there's no nicks in the molecules, which might pose toxic effects in and of themselves. We just don't prefer multi-wall. But as far as industrial applications, there's really no limit to the amount, and there are a number of companies, Southwest Nanotechnologies in Oklahoma, for example, that's all they do is make gram quantities of carbon nanotubes.
How big a string would that make?
I don't know, because the tubes vary in their length. So we haven't performed any studies at cutting the tubes down to size, because we really don't care how long they are as long as they bind to the cell.
Thank you.
Last question, please. Yes.
Ben Mann with Medtronic. I actually thought it was a fascinating talk, and I think you're really doing
Thank you.
this is going to be plagued with some questions and technical difficulties. One question for you, going back to the energy source again, I think we've all got a lot of experience in RF. Have you considered going into cryo and seeing if does the nanotube very specific to in the spectrum, in the radio frequency spectrum of the
I can't say that we have. We've
Okay.
focused on what we know works now, which is the thermal ablation, the 13.56 megahertz RF, and the 820 nanometer near
Range,
IR.
okay.
So we haven't gone the other direction.
Okay, because I might talk to you afterwards about some possibilities. Okay.
Very creative, outside of the box thinking, Ben.